system. So today's session is more of a knowledge sharing session of what I have learned while working with a distributed and decentralized system. So the goal of today's presentation is to give you an idea of how the consensus algorithm work in distributed system and decentralized system, and why the algorithm used in distributed system cannot be employed in decentralized system as it is without any backing model. And you'll also see the direction in which the decentralized system is moving towards. So can I know how many of you here already know what blockchain is? Wow. Almost everyone. So I'll make this session informative as possible. So for sure, it's creating hype in the digital world, and the goal of all the company in 2018 is to look into blockchain technology and see how they could leverage this technology to create next generation of decentralized application. And the technology as such is truly a breakthrough technology in the infrastructure layer like TCP and IP. And it can be used for many use cases like where multiple parties are involved, like supply chain management, for instance, or cross-border payment could be another very good use case for blockchain technology. So today's agenda is, I'll start from the basics of a centralized system to distributed system, and then we'll move into decentralized system, and then we'll see the core of the system, the consensus algorithm. And we'll see in detail about some of the consensus algorithm like Raft, proof of work, and Hashgraph, and finally we'll end with the demo of Hashgraph. That's getting trendy these days. So centralized system, it's an old way of architecting your application. As you might be knowing, it's like keeping your application state in a single server. So when the server is lost, your data is lost forever. So whereas with the distributed system, it's like you'll keep your data on multiple servers. So if one of your server data is lost, you still can get it from another server. So distributed system, if you look at the whole thing, it's controlled by a central entity. So if the central entity tomorrow decided to shut down the system, he can do it. No one can do anything about it, or he can choose to alter the data. So we basically trust on them to keep our data safe. This in contrast to decentralized system, like your data, once the server is up and running, you cannot shut down it without the public consensus. So decentralized system, it's like you don't know your participants. Anyone can join the community and leave whenever they want. But with distributed system, you know who you are talking to, who you are storing the data with. That's a major difference between distributed and the decentralized system. So since we have multiple copies of data, we have to make sure that the data in all the servers are same. So consensus algorithm came into picture to keep the data in sync within the servers, with different servers. So the first consensus algorithm is Paxos. It was discussed in the paper part-time parliament in the year 1988. If you look at the paper, it's quite complex to understand. So the algorithm as such is quite complex. So people came up with a more understandable version of consensus algorithm called Raft. That's a ladder-based algorithm. So we'll see how the Raft algorithm works. And then we will see the proof of work algorithm, which got famous in the decentralized world after 2008, after the Bitcoin thing came into existence. So, and then we'll also see about Hashgraph. It's a recent consensus algorithm, and people believe that it's going to be the next version of decentralized systems. So Raft consensus algorithm, the node can be in one of the three states, like it can be in leader state or a candidate state or in a follower state. So imagine, to understand the algorithm, so when you start your cluster, all the nodes will start in the follower state. So if a follower didn't hear from the leader, it will try to elect himself as a leader by sending a message to its follower. So when the follower reply back with their votes, when the leader get enough votes from the follower, it became a leader. Like the candidate become a leader. So when it becomes the leader, all the data transaction goes through the leader into the cluster. So for instance, let's say a client wants to store a data D1 into the cluster. We will first send it to the leader, and then the leader will distribute the data to the follower. And the follower will acknowledge back about the receiving of the data. So when it get enough acknowledgement from the followers, the leader will first write the data into its own ledger and then will ask the follower to do the same. So now the system is in a consistent state. Look, so everyone know about the data and the cluster is in a happy state. So this voting based algorithm will work very well as long as majority of the node is up and running. So it's like if you take a cluster of 5 nodes, if 3 of the nodes are up and running properly, then the system will work very well. But if more than 1/3 of the nodes are malicious, then the system will crash. So this is an open research problem. This is the best the distributed system can work. So 2/3 of the node has to be honest. It's a rule of thumb. So imagine that you take this simple Raft voting based algorithm and put it on a decentralized system where you don't know your members, where you don't know your players, who you're talking to, where you are storing the data. So what could go wrong? Like one of the obvious thing that you could see is like it's a leader based algorithm. So the throughput is limited to a single node, the single leader node, but it's not that very intense. So some application can live with the slow progress. So what else could go wrong? Like one of the major disadvantage of this voting based algorithm in decentralized setting is it's susceptible to Sybil attack. So what is Sybil attack? It's like a single node can spin up thousands of nodes and break the consensus by scanning up to more than 1/3 of the network easily. So if an attacker want to hack the network, what he can do is like he himself can ask the node he spawn up to elect himself as a leader. So now the malicious node as a leader control what goes into the cluster. So he can decide and disrupt the consensus fully. So these algorithm cannot work as it is on a completely decentralized system where all the nodes are same. So what we need is like, we need some algorithm that makes it very difficult for the attacker to break into the system. So that's where POW comes in. So POW was the first, was introduced for spam filtering, and then it was adopted in 2018 for a decentralized system. So proof of work is a computational puzzle. So the idea of this algorithm is quite simple. It's like you have to find a random string that satisfies a mathematical property. So the mathematical property is like the first few bits of the string should start with 0. The only way to come up with this kind of string is to trial and error, through trial and error. Like see an example of how it works. Like for instance, let's imagine that you want to store the string Voxxed into your cluster. What you do is like you have to take the challenge string and then find a proof string that satisfies the resultant string mathematical criteria. That's for this case, the 4 bits of the string should start with a 0. So when you take the challenge string and proof string and put it into a hashing function and see the resulting string, if the resulting output string matches the resulting string, then you have to publish your proof string along with the data into a cluster, and the cluster will validate your proof string and the transaction. If it's valid, it will be added to the server ledger, nodes ledger. So the way to do it is like first you take the challenge string and then you use the proof string as 0 and check if the resultant string coming out of the hash function matches the criteria of the resultant string. If it doesn't, then you do it again. If it doesn't, then you do it, increment the proof string and see if the criteria matches. If it doesn't, then you do it again. So you'll stop when the resultant string matches the output string that comes out of the hashing function. So now you got your proof string. So what you do is to publish your proof string to other nodes in the network. So when the cool thing about this algorithm is like it's very hard to find the solution, the proof string, because to give you an idea of how hard it could be to get the first 40 bits of the string to be 0, you have to try almost 1 trillion times. So it's very computational intensive task. So but the but you can verify the proof very easily by what the node validator has to do is like they just have to take the challenge string, they have to take the proof string and see, concatenate them together and put it into a hashing function and see like the hashing function will be SHA-256 and see if the resultant string matches the mathematical conditions. If it matches, then all the node will add it to their ledger, and now the system is in a consistent state. So as you can see, like this algorithm is very time consuming. This algorithm is used in Bitcoin, and as of now it's taking around 1 minute to add a block into the ledger. So it's very time consuming process, like algorithm. So, and it's also energy consuming. Why? Because SHA-256 is irreversible. So if you look at the basic principle of thermodynamics, it's like if any process is irreversible, the process has to spend a certain amount of energy for sure. So this algorithm cannot be enhanced to a level where it's consume less energy or it's consume less time. So principally this algorithm cannot be efficient. So and the timestamp given by this algorithm is not fair. Why? Because the node who find the proof string will decide the timestamp of the data that goes into the cluster. So it's like a single node can drag the timestamp to a very great extent. So it's not asynchronous Byzantine fault tolerance. Like asynchronous Byzantine fault tolerant is the strongest form of security that you can get in a distributed or a decentralized system. So and another drawback of this algorithm is it gets secure over time. So it's like it's a leaderless system, so anyone can work on the problem and find the proof string and publish to the network. And the longest chain at any point in time is considered as a source of truth. So you cannot say at a point in time, like with the probability 1, this is the state of my application. It gets secure over time. And the system is susceptible to 51% risk, like the same as the distributed system. 2/3 of the node has to be honest for this algorithm to work in a decentralized setting. So if you look at distributed ledger technology in whole, the first version of distributed ledger technology, it's slow. It cannot be scalable, or we cannot make it faster to process millions of transactions per second. So why? Because the nodes have a flat hierarchy. Like all the nodes will have the data and all the nodes will validate the ledger state. This in a way is like very first of all time consuming, and also it consumes a lot of server power. So this first version of decentralized system is not suited for a real world application that involve a lot of data to be processed in second. And also, like since it's fully decentralized, the power is in people's hand. So anyone can choose to come up with their own blockchain technology, or can come up with their own coin. So as of now, there are more than 1,600 coin in the market, and we have 6 version of a blockchain technology. So it's getting very chaotic in the open source world, like for decentralization. So what we need is, like, it feels like we need a governance model to watch over our public ledger, just like the government overseeing the public. So Hedera Hashgraph comes up with a governing model, and also it implements sharding to watch over the public ledger. It's like their governing model is it's like a open consensus and a permission governance model. So what it means is, like, they have more than 39 members across different continents running the node, and we'll see if the public ledger is behaving in a consistent way or not. And here the nodes are organized into groups. It's not a flat hierarchy anymore, and the groups will be responsible for holding some amount of data. If data required for a particular shard is not available in the shard, then a shard can communicate with another shard. So inter-shard communication is also possible with the Hedera Hashgraph. So the sharding, the consensus algorithm used inside this sharding is a virtual voting based algorithm. And it's good to see the trend, like again we are going back to a voting based algorithm which was used in the very beginning of a distributed system. So the way the gossip based voting algorithm work is like you share, a node will share whatever it knows to another node, and the node then will share whatever it knows to another node, and the gossip will spread over time, and eventually the system will reach a consistent state. So I'll give an example of how it works. So the node will exchange message in the form of events, and the event is a data structure that consists of timestamp, transaction, and the previous transaction hash. So let's say the client want to store the data into the cluster. It will first send to a node, and the node will pick a random node and share the information with that node. Now the information known to node 2 will be shared to node 3. Like now in this case, node 2 will send 2 events, one what it knows and one what it got from node 1. Now node 3 is aware of 2 events in addition to the one it knows. So now the node 3 will share whatever it knows to node 1. And then the process goes on, and eventually the system will reach a consistent state. So if you look at this algorithm, since it's a leaderless system, it's not possible to do a denial of service attack, and the timestamp given by the algorithm is very fair. Why? Because it's not a single node controlling the timestamp. The way the timestamp is decided for the data is like you take all the events and then take the timestamp from the events and sort it down in a descending order and pick the middle one. So even if single node is malicious, he cannot drag the time, even if he say the transaction was published in a BZ, since we are sorting the timestamp in descending order and getting the middle one, it's the timestamp cannot be a fake one. And it's not energy consuming. It can process as many transactions. It's limited to only the bandwidth. So if you have a high bandwidth, then you can process many transactions in seconds. So if you look at the decentralized system, if it has to work for a real world application, then it has to be both performant as well as secure. And Hedera Hashgraph already have a very strong foundation for security, and they have a mathematical proof for their algorithm for being asynchronous Byzantine fault tolerant, and their white paper described almost all the scenarios, components needed for a decentralized system, but all the guidelines of it's neatly done. So maybe it's people are thinking this kind of system as a future of a decentralization. So if you are interested in Hedera, the way to start is like you could go to Hashgraph website and download the jar, SDK jar, and then basically you have to implement 2 classes given by the SDK. One is the main to initiate the platform, and another is the application state. To choose the way you want to store your state. With Ethereum or any other thing, the state is automatically stored to your file system, but here you can choose how you want to store your state, either to your file system or to your database or whatever. So I will go to a demo. So the demo will in the demo I'll show how to publish a transaction into the platform and reaching consensus. So here, my project structure is like this. That's my SDK of the Hashgraph, like the library required for the consensus algorithm or everything in here. And then the config, in the config.txt, I'm spinning up 4 nodes. All of them are running on my machine, so that's why you see the port different from one another. So if the nodes are running on different machine, you have to type in your IP in here, and followed by the port can be the same one, and this is nothing but a name of the node, Alice, Bob, Carol, and Dave. And once you have your configuration ready, what you have to do is like you have to implement the two classes, Swirl main, to initiate the consensus platform. So here I'm initiating the consensus platform, and then what I'm doing is like when the platform is ready, I'm getting the name of my node from the address book from the configuration in here, Alice, and then pushing the name as a transaction into the platform. So here the platform.create will push the transaction into the cluster. So when I do like platform.create transaction, what it does is like it will first announce the transaction to all the node in the cluster, and then when it reach consensus, it will call back this method in the class swirl state, like handle transaction. You'll have a method called handle transaction. So here you can choose the way you want to store this data, like to a file system or to a database. So I will run this algorithm, and I will run the application. It will take some time to initiate the keys for each of the node first, and then it will start up 4 nodes as mentioned in the config file. That's why it's taking a bit of time. Okay. So here we have it's not clear, so I have the output on my presentation. I'll show it in a bit. So what you see is like the output from 4 of the nodes, and the consensus order. The final one is the consensus order. So I'll go back to my presentation where you can see the output clearly. Like here you can see like the node 1 first will know only about only about one transaction, and then eventually it learn about another transaction, and then it learn about another transaction. And if you look at the final order, all of them is in the same, like for node 1 Alice, Carol, Dave, Bob, and the node 2 it's Alice, Carol, and Dave, Bob. So this way the system will be in sync with one another. So yeah, no, that's all I got for today. So if you have questions. Yeah?
Is there any coin that is based on this Hashgraph?
Client?
A cryptocurrency coin?
No, not cryptocurrency yet. Their public version is not released yet. They are planning to release their public ledger by end of the year. So no cryptocurrency yet, but there will be a cryptocurrency for sure. Yeah.
You see, Hashgraph is actually a closed source. So it's patented because the guy who started this is from CMU. And this 39-member council, you don't know what's going on inside there. And why they can raise money is all because of those companies are publicly listed companies, the name that we are all familiar with. So you don't know what kind of thing they do inside, because people from outside have no clue. They can claim anything, and they say they are ACID proof. How do I know you are ACID proof, ACID compliant, unless I get hold of everything and build everything from scratch? So the POC is actually a very deceptive model. And also, this is, they claim they are graph, but the very fact that if you are DLT, you are not exactly graph. I mean, I did a study, comparison between IOTA, which is actually a database, but they run the machine behind it. They have a scalability problem. So versus Hashgraph versus there are two others in the graph space. So I can't see what stands out from Hashgraph. And currently there are a lot of developments in this space. So I'd like to hear your view. What makes you think that Hashgraph is outstanding?
It's because if you look at the governance model, it's from, as you were saying, like it's from a different country, the different companies from different country who has experience in DLT. They are billion-dollar companies, so they don't have they shouldn't have.
Million-dollar company. A lot of things come from open source.
But it's not a single node deciding to alter the data. It's like the 39 companies as a whole will come to a conclusion whether to change the state or it's like the 39 members will take care of the assignment of nodes to the shards first. It's based on a proof of stake model, and it's like you could think of it as a permission ledger governing the public ledger. If it's a fully public ledger, then we can already see like it's becoming chaotic. Like we created so many cryptocurrencies, and if you look at the coin market cap, we are trading almost more than 1,000 currencies. So there should be a governance model overseeing the public ledger for these kind of system to scale up. You could think of it as a it's a system that's laying down the rules needed for the system to evolve further. Like for internet or for World Wide Web, we have a system to write down the standard. Yeah, W3C.
The same way. WTC totally open. It's very transparent. And this consortium, they play the game with money. And you don't know what's going on inside. I'm serious about this. I raised this question to Stuart when they did the launch. So I'd like to hear your view. So it seems that your view is that you believe in a thing called consortium just because they are very big.
It's like the members of the council is not permanent throughout. The member will change every 2 years. So
but 2 years you can have problems. In technology, 2 years is a very long time, especially in blockchain.
But the thing is, like, if you like to examine their code, you can raise a request to Hedera, and they are open to give the code base to you to get your opinion. So they are pretty much flexible in their in the way they do it. That's what I think.